Here's another video for the lecture intropde. In this video we present section 5.4. In this section we calculate the solution in dimension 2. This is now a new method how to calculate the solution in dimension 2. We introduced the so-called method of descent. So this means we transform, so the method of descent. Transform the initial value problem of the two-dimensional wave equation into an initial value problem of the three-dimensional wave equation. And then solve this three-dimensional problem, and then we see that we can read off from the solution of the three-dimensional problem. We then can read off the solution of the two-dimensional problem. Okay, how to choose this initial values in three dimensions. So we have functions. We have functions G and H. We call this G and H. We have G and H. These are functions on R2 to R. And now how to make then functions on R3. We define a map. We define a map which goes from, and we call it bar. This goes from R3 to R2. X, which has the component x1, x2, x3, is mapped to just taking the first two components. This means we forget the third component and then just have this map. Now we define new functions, and now we look for a solution, solve the following problem. In dimension 3. Wave equation minus Laplacian u, here of course at x and t. X and t is 0 on we call it u bar on R3 cross R plus, and we have here square, and then we also have that u bar of x0, this should be just g of x bar, and du bar divided by dt of x0, this should be just h of x bar. Because in this way, the composition of this function or this mapping with these two functions, they give, of course, functions on R3. So this is the way how we make the initial values in R2 to initial values in R3. So this clearly means that the initial values d by dx3 of g of x bar is 0. So they do not depend, and the same for h on the third component. Yeah, this is 0. Now, if we have, now we claim that this, whenever we have a function, also if, let's make a general discussion, yeah? If f is a function on R3, which does not depend on x3, or x in the third coordinate, the last coordinate. So this means that df by dx3 of x is 0. Yeah, then of course the same holds for the mean. Yeah, then we have, let's calculate d by dx3, and now we take the mean integral over the boundary of the ball with radius x and r, f of y d sigma of y. Yeah, how, again, we want to make this that the domain doesn't depend on this coordinate, so we transform this, and then we can calculate dB of 0 r f of x plus y d sigma of y. And now we can do the calculation d by dx3, because the domain now is independent of x3. We can put it in the integral, and then we see this is 0, yeah, because this is 0. Yeah, it just applies here. So this means the function x going over to yeah, here this all should be the means. Of course, the function which goes to the mean, over the boundary of a ball, y, this function also does not depend on x3. So that, but this means if a function doesn't depend on x3, yeah, then it is a function then it is the composition. Then it is the composition of x going over to x bar with a function on R2. Yeah, and now we do exactly this procedure for the solution of the wave equation. Okay, let's do the calculation. Yeah, by these formulas, so by Kirchhoff formulas, we see that the function, that the solution of the three-dimensional wave equation with initial values, yeah, we just take as the initial values x going over to gx bar and x going over to h of x bar. Also, do not depend on x3. And so they are, so this means so they are of the form u of x of this form with some function u on R2 cross R plus. Yeah, and this u solves the wave equation, the two-dimensional wave equation. Why? Yeah, because since this function u, the solution, we called it u bar. Now, if we calculate, then we see that dt of u from u bar of xt minus Laplacian u bar of xt. Since this doesn't depend on the third coordinate, we can write this u tilde of xt minus, and then we only have the squares of the second derivatives of the first two coordinates, u bar of xt. Yeah, since this the derivative with respect to x3 is 0. So we see this. So u indeed solves two-dimensional wave equation. Now, how to calculate? Now, this is quite easy. How to calculate? We may evaluate. How to define this function. In order to calculate u of xt, we may just evaluate u bar of xt at any point x, and here we use any coordinate x3, any coordinate x3. Yeah, so this means x and this and the easiest choice is of course x3. So we take x3 equals 0. So we just evaluate u bar at x0 t. Yeah, and this is our definition of u of xt. Okay, so let's do the calculation. So what comes out? So we get u of xt, our solution of the wave equation is now just now let's do first the calculation for this means. Yeah, so we have to calculate such means. Yeah, and how to calculate such means. Yeah, now we calculate calculate. So we need to calculate this expressions here of g of y bar d sigma of y. Yeah, where dB of xt should be the ball, should be a ball with some coordinate, yeah, x3, where we, yeah, so three-dimensional ball. So how we choose this ball as x0 and then with radius t. Yeah, so this ball here the boundary of x0 t is the three-dimensional ball, is the boundary. It's the boundary of the three-dimensional ball, is the boundary of the three-dimensional ball with center. Yeah, and the center is now x0, where x is our coordinate of R2 and 0 we choose, and radius t. Okay, let's do this calculation. And for this, we again use our parametrizations. Yeah, and we may use, we do the following. Yeah, the two-dimensional ball, also let's draw it here. Let's have here the plane, in this plane. Yeah, then we have here, this is the two-dimensional ball. This is the two-dimensional ball, bxt. Sorry, we call this bx. Yeah, this is the two-dimensional coordinate we call bar. Okay, and over this ball we have the spheres. We have two spheres, two hemispheres. Yeah, we have two hemispheres. And we parameterize these hemispheres by the map phi, yeah, which maps this two-dimensional ball to the boundary of the three-dimensional ball. And how we define this, also we already did this, now we define it by y going over to the vector y, and as the last component we take plus or minus gamma of y, with gamma of y is clearly square root of t square minus y square. Yeah, so t square minus y square. So we have this function here. Okay, since we want this ball, we define it differently. We subtract here, of course. Yeah, so we take y minus x bar square. Yes. And then we already know, sorry, we call this psi, not phi. This we call psi. Yeah, and we already know how the determinant of, also if we look for the derivative, now we look for the derivative psi prime of y transposed psi prime of y determinant. Yeah? This is again of the form which we had already seen, yeah, in this definition. And then this we had this formula. This is gradient of y gamma of y square. Yeah, and this is the formula. Now, what is the gradient? Yeah, gradient y of gamma of y. Now, this is easy to calculate. We get y minus x bar square root of t square minus y minus x bar square. So this determinant, yeah, then 1 plus gradient y of gamma of y square. This is, of course, t square minus y minus x square. And now we bring this on, we bring both on the same numerator. Then we have, for the 1, we have t square minus y minus x bar square. Minus the square, we get plus y minus x bar square. You see, this cancels, and we obtain t square minus y minus x bar square. So the square root of the determinant, yeah, the square root of the determinant is now the square root of things. So we have 1 plus dy gamma of y square, and no, only this term square, and the whole thing we take the square root. This is, of course, since t is positive, it's t divided by square root of t square minus y minus x bar square. Okay, now we introduce our formula. Yeah, okay, so what is the mean? Now we can do the whole calculation. d of xt, g of y bar, this is what we want to calculate. Of course, what is the volume? Yeah, the three-dimensional sphere has 4 pi r squared. So the volume is 4 pi squared t squared. Yeah, this is just for the mean, 1 divided by the area of this three-dimensional sphere. And then we should take the integral over b of xt of g of y bar. Okay, now we have this both. Now we have the upper hemisphere and the lower hemisphere. And with both signs, also for plus we get a parametrization of the upper hemisphere, and for minus we get the lower hemisphere. Of course, the equator here, this is neglected, but this is a set of measure 0 inside the sphere, so we can neglect it. And then, so what we get? Now we get twice, yeah, because we need the upper and lower hemisphere, so we get 2 times 4 pi squared t squared, and then we get the integral over this two-dimensional whole ball, not the boundary, now times g of y. Now we are in 2 dimensions, and we should multiply with this function. Yeah, so we get t and dy square root of t square minus y minus x bar square d2y. d2y is this now. Yeah, because now we use this parametrization, but since the function g doesn't depend on the fourth coordinate, so it doesn't depend on the height, on the third coordinate, which is the height here in this picture. So this here is the third coordinate. And it doesn't depend, so it takes here and here the same value, and it takes at all the same values yet then inside this ball, this whole two-dimensional ball. Okay, so we have indeed this simple formula here. And okay, now we can put out the t. We can put out the t. And cancel the 2 and this t, and so we get 1 divided by 2p square. Sorry, it's not p square. The volume is 4 pi. 4 pi. So it remains 2 pi. Sorry. Yes, 2 pi and only 1 t. Yes, 1t integral over this two-dimensional ball g of y t square minus y minus x bar square d2y. Okay, now we insert this formula in our formula for the three-dimensional wave equation. So what we obtain? So we obtain u of x bar t. This is now, so this is now the two-dimensional solution, and this is clearly. Now let's recall the three-dimensional solution, but we don't take the final form. Sorry, we take not the final form, but we take this form here. We take this form. Remember this. Okay, so we should multiply by t, and then so now we insert this form, and this. So this is d by dt t times, this is g tilde, g of y t square minus y minus x bar square, and here we have the ball xt, two-dimensional ball, plus t, again two-dimensional ball, h of y d2y, and again this and again this formula times t. So sorry, I forgot an important step. Now finally t, since this is again the mean, we get t, sorry, here we forget. Finally, now we want to transform it to the mean, and then we get again this 2 pi, but it's now the two-dimensional ball has volume pi times t square. So this is now 1 divided by 2, and of course, since we have only one t, to get t square we need an additional t. So in the top we have a t, and now it's the mean over the two-dimensional ball. That square root of t square minus y minus x bar square. Okay, so we have this 2.5. Yeah, and now we should keep in mind, yeah, that we should take twice. Yeah, so here we only calculated the means, yeah, and yeah, we inserted this and get this, and now we insert this in our formula for the two-dimensional, three-dimensional wave equation. Yeah, so we should insert this here in these two formulas. So this means, yeah, now we use these formulas to simplify these expressions. Yeah, so we have this. Sorry, we should first calculate. Yeah, and then we get an extra factor t over 2. So we get t square over 2, and here we also have t square over 2. Yeah, so now we have this formula. And now we do the same calculation as before. In order to derive the derivative with respect to t, we make this independent of t only in the first term. And to make this independent of t, yeah, we do the following. d by dt. Then we have t square over 2, mean value. Now we take the ball, of 0, 1. And then we have to, of course, insert g of x, yeah, x bar plus, and now t times z. And here, if we insert this, then we get square root of, and here we have t square z square. d square z. Since we have the mean, we have no problems with the transformation. This term we leave as it is. Of course, here is missing t square minus y minus x. So here h of y, d square y, square root of t square y minus x bar square. So now here we have an additional t, and t is positive, so we can put it out of the square root and cancel it with this term. And then we get d by dt, t over 2, t over 2, mean value of g of x bar plus tz divided by 1 minus z square. dz square over the unit ball plus this term we leave as it is. Of course, mean value h of y d y minus x bar square. Okay, now we can do the calculation. Now we do the derivative. This is, of course, 1/2 g of x bar plus tz, 1 minus z square dz, and the other term plus t over 1/2, and then we can put it in the integral, the derivative, and calculate it. And then we get g of x bar plus t set times set gradient. And of course, this stays as it is, doesn't depend on t. Yeah, this is nice. D square set and plus, of course, the term with the h. Square root t minus a bar square. Okay. And now we do the transformation back. Yeah, and again write this as integrals over here this should be, of course, the integral over the one ball, integral over the one ball, and integral over the xt ball. Now we calculate this back. Yeah, then here this is a 1. Yeah, then we get this extra factor back. Yeah, so for this reason we get an extra t back. And then we have this ball xt, and of course we get here, now we combine this term and this term, and then we have, so we have g of y plus, here we have an extra power of t times h of y, the whole thing d square y, and here square root of t square minus y minus x bar square. Yeah, of course, you should keep in mind that we here had to transform back the set. Yeah, this we have to put in 1t back, and putting in this 1t back here in the bottom term, this gives an extra t here. Yeah, this is why we get here this extra t in front of the g. And here we do the same. Yeah, plus, and then we obtain here we put the t to the set. Yeah, the t to the set, and then but we get back one extra t from here. So we get gradient of x bar plus t set times y. Now we get back y, and times y minus x bar, of course, divided by t square minus y minus x bar square root d2 of y. Okay, and this is here this formula. Yeah, this is this formula. So we obtain at this formula, and this is Poisson's formula. For the solution of the two-dimensional wave equation. Yeah, the initial value problem. Okay, finally we just make some observation. The first thing is that it depends not only on the boundary of the balls, so u of xt depends on the values of g and h, so in the initial values, on the whole balls, and not only the boundaries of these balls. Yeah, as in dimension 3. Yeah, so let's draw again this picture. Yeah, so here we have our we are in 2 dimensions, yes, and this is time. So we have here x1, x2, and so we have here some point. Let's see. Yeah, some coordinate, and here we have the time. Okay. Yeah, so this is the time, but this means at this point here, then we obtain the whole ball in this plane. It depends on the values of the whole ball in this plane here. And this means if we connect all the points on the ball, yeah, with these points upstairs here, then the velocity the absolute value of the velocity is bounded by 1. The length of the velocity is bounded by 1 and not equal to 1 as in dimension 3, and not equal to 1 as in dimension 3. Yeah, as in dimension 3. Okay, we will later see that this generalizes to all even dimensions. Yeah, and okay, so what we have done today, we introduced the so-called method of descent. So we transformed the two-dimensional initial value problem of the wave equation into a three-dimensional initial value problem, where we took in the 3 dimensions initial values which do not depend on the third coordinate. And then we showed that the solution also do not depend on the third coordinate, so it comes from a solution in 2 dimensions. And then by this way, we calculated the solutions and obtained finally Poisson's formula. Yeah, we obtained finally Poisson's formula for the solution of the initial value problem of the two-dimensional wave equation. Thank you.